Admitted to class. Today is the 27th edition, and we are going to tackle a new concept today, which is the concept of Rambach integration. But before that, I would like to quickly recall what we did yesterday. So let me share the new slide with you. So what we did yesterday, we went through the derivation of the error term for the trapezoidal rule, this one, and the Simpson rule, if you recall. We used the formula for the composite integral, composite trapezoidal, composite Simpson rule, and we use the local error, right, of the original rule when we are working on a smaller subinterval, right? And then we use a summation, we sum up the error term, and we show that the error term will end up being of this form. You can see that this error term is fourth order, and that is for the Simpson rule, and for the trapezoidal rule is second order. As you can see, as you can see here, second order for the trapezoidal rule, and fourth order for the Simpson rule. And after that, we tackle the same example. Recall this example. We use this same example of f of x equal to 2 plus sine 2 square root of x over the interval 1/6, closed interval. So we use the exact value of this definite integral to evaluate the error term. We just use the definition of a quadrature rule, whereby the integral is equal to the root plus the error term. So from that, we extracted the error term, which would be the difference between the exact value of the definite integral minus the rule, the trapezoidal rule in this case. Since we can evaluate, we know the rule, the trapezoidal rule. Now, so this is a case that we know. So we apply it and we compare our result with this second order accuracy of the trapezoidal rule. Wait, where am I? Now this is T trapezoidal. So we compare with, because we know that the order of accuracy of the error term, the error term is big O of h squared, meaning that the order of accuracy of the rule is second order. And that's what we try to explain here. Below the table, we try to explain that actually the observation from this computation agree with the second order accuracy for the method, which you can see here. Okay, so that's what we did as an application. And the second application was to use the actual expression of the error term to find the number of subintervals or the step size h for which the definite integral will give us a result that will be that will be less than, right, where the error will be less than 5 into 10 to the negative 9. So this is like our tolerance. So that's what we did. And for that, we use the actual expression of the error term for the Simpson rule. This is the formula for the error term. You can see this formula. This is the formula that gives us the error term. So we use that expression. We find an upper bound of that expression, of course, the smallest possible upper bound. which we obtain to be independent of psi, because psi is not known. So we cannot apply the constraint, that is error less than 5 to the 5 times 10 to the negative 9. We cannot, if we do that, we will be stuck because we don't know psi. So for that, we need to find an upper bound that will depend on h only or on n only, and that's what we have here. And it is to this upper bound that we impose the constraint, this constraint. So if we impose that constraint, and this is the case here, you can see that we're imposing that it is the upper bound that should be less than the constraint. Why? Because if this upper bound is less than or equal to the constraint, automatically the error will also be less. So this is a step that is very important to understand and to follow. Otherwise, we'll be stuck. And something else that I would like to point out here is that this procedure is not unique, meaning if you have a different problem, you will not proceed exactly this way. When I say this way, the upper bound, you have to do that. You have to find an upper bound. That one, it is almost compulsory, if you can see. But the way you proceed to obtain the upper bound, that is what I say is not unique. Because obtaining the upper bound is just a problem of optimization. Optimization problem. If you know how to find the maximum of a function, because this is what you need to find. There are many methods to find the maximum of a function over an interval, and that's what we are doing here. So the step toward obtaining an upper bound on the error term is optimization. And for that, you can use the first derivative test, the second derivative test, anything you want, provided you obtain the maximum of the derivative, this fourth derivative, because you need this fourth derivative. Of course, for the Simpson rule, if we are using the trapezoidal rule, then it will be the second derivative. And you know, and you will agree with me that finding the maximum of a function, there are many methods depending on the structure of the function. If the function is simple to compute, you can just look at the function and know exactly how to proceed to get the maximum. So here we use this procedure because of the structure of the fourth derivative. You can see this is the structure. So because of that, that's why we proceeded this way. I'm saying it because I realized from past experience that regardless of which function you give to students, they will just follow this procedure, which is wrong. Right? Right. Because why? Why? Because here for this function, we can see that the maximum here is attained at 2. And what is 2? It is this point. Now, somebody will read this. Any function that you will give, you will take the left-hand side and apply the function there and say that that is the maximum, which is wrong in general. It is possible here because the function is a decreasing function. And if the function is decreasing over an interval, then you know that this left value will give you the maximum. That is the only reason why we proceed that way here. But it is not a silver bullet that that procedure, you will not use it everywhere. No, no, and no. Go back to your optimization course to know how to find the maximum of a function. So if the function that is given to you has a particular structure, follow whatever procedure you need, provided you obtain the maximum of that function in absolute value, because you need the maximum of the absolute value. So the function will be positive. So I hope this explanation is clear. I really want to stress on that so that it will be clear for everybody, those of you who are currently watching, and for those who will be watching later on the recorded video. Okay, so once the upper bound is obtained, you just impose that condition on the upper bound, which will automatically implies that this condition also will be satisfied. That is the error term less than the condition. Okay, the rest, once you do this, the rest is just solving an inequality. And that is it. So that's what we did yesterday. Good. Now I will introduce the concept of round-bar integration. I think we did something similar in the first semester related to numerical differentiation. I don't know if you really went, but it is in the note. In the note for numerical differentiation. But I think we cover that. So the principle is the same. The principle is exactly the same as you will see. Yeah, that was differentiation. Yeah, we did the differentiation, but this time talking about integration. So the principle is the same, and what is it? We know already that our rules, like in this case, we know that the trapezoidal rule, composite trapezoidal rule, order of accuracy is 2, second order. Simpson's rule also, composite Simpson rule, order of accuracy is 4. That is a fact, it is none. So meaning that each time you apply those rules, this is what you will get. Second order accuracy for the trapezoidal, composite trapezoidal, you have second order accuracy. And for the Simpson rule, you have fourth order accuracy. And for Bool's rule, you have sixth order accuracy. In other words, it means that you cannot modify that order of accuracy if you apply the formula directly. It will be like that. But now the procedure which is here called Richardson technique, right? Obviously, when you apply that Richardson technique to this, the process is called Romba integration process because you apply it to an integral, right? Because the rule that you'll be using is an integration rule. So you use the Richardson technique in order to improve, because the purpose is to improve this. Not just to say, okay, this is the order of accuracy, there's nothing we can do, we leave it that way. No. We can still improve this using a particular technique called Richardson technique, right? That Richardson technique is what we apply. And how does it work? First of all, if you, let us concentrate on the trapezoidal, right? The trapezoidal Simpson, what am I saying? The composite trapezoidal rule. The error term is second order accurate, meaning that if we expand this error term in terms of h, we obtain an expansion of this form. Because remember that the order of accuracy gives you the smallest exponent of h in the expansion of the error term. So meaning that for the trapezoidal rule, the leading term here will be in h squared. And then it will continue. So we have these many terms. And what you can realize here is that all the powers of h here are even powers of h. Means they're even powers. So in other words, if I want to perform the Richardson technique, the purpose of the technique will be to come up with a strategy that will allow me to cancel out this A1 term in the expansion. If I succeed to cancel out this A1 term, the next term will be h to the 4th. So we'll be improving the accuracy from second order to fourth order. And we can proceed with the technique to higher order. So roughly speaking, that is the procedure. Or, I mean, that's the idea behind the procedure. Now, in order to perform that, this is the combination we perform this is the formula. The technique, in fact, is summed up into this formula. As I said, when we perform this technique, the purpose is to eliminate this first term, to zero it, and get the fourth order accuracy, which is what we will get here if we perform this technique to this trapezoidal Simpson composite trapezoidal rule. Okay, now let's look at what this formula tells us. What does it tell us? We have the trapezoidal rule, which is given by this. We are going to use, or we are going to estimate this same integral, using successive values of h. That is, we use h and h by 2, or 2h. We can half or we can double, which is in a certain manner the same thing. So that's why we called it the ratio, the 2:1 ratio. Meaning that if currently it is 2, by halving, it becomes 1. So if I use h, next time I use h by 2. So I'm halving. Or if I'm using 2h, next time, if I have 2h, is h. So that's what we call the 2:1 ratio. So that's what we do. But how do we proceed? So we compute this t, we take the rule, this one, tfh. We take a particular value of h, which we fix. We obtain a result, and then we have the same h, and we recompute the integral, but with a finer h, meaning that if we have h, we will obtain a better result. Because remember that when h goes towards 0, your rule will give you a better result. We did something similar when we took the limit, right? So that's exactly what is happening here. So this ratio 2:1, we compute the rule for h, and the next time we use the same rule but with h by 2. We obtain two different results. The first result for h will be less accurate compared to the second result for h by 2. Therefore, we have here, if you look at this, we have the more accurate result, which will be the one obtained with h by 2, and we have the less accurate, which will be the result obtained with h. Now, if we use those results and perform this algebraic manipulation, the result that we obtain here will be a better estimate of the integral. And theoretically, what we obtain a result which is fourth order accurate. Okay, so that is for the explanation. Now, let us look at an example. Is it clear for everybody, the explanation, before we proceed? Can I proceed?
Yes, doctor, may proceed.
Good. Now, let us look at this particular example. We want to integrate this function, exponential of negative x squared, over the interval 0 to 1, 5. Right. So we are going to use the Romba integration to find this definite integral using what? We are going to use the trapezoidal rule. Are we using trapezoidal or Simpson? I think it's the Simpson rule, right? Because here I see 2. H by 2. Wait. Which rule are we using? Is it trapezoidal or is Simpson? H by 2. Okay, this is 0 to, okay, I think this is, this looks like Simpson rule. No, this is the trapezoidal, it's not Simpson. This is the trapezoidal rule. Let us look at, since we only use 2 terms. Yeah. This is the trapezoidal rule. So what is done here is it is the composite, right? Because if you use the trapezoidal rule, trapezoidal rule, you take the summation, you sum up the term. This is what we'll get. We'll get this. So you can see here, we have h by 2 here, f of a, f of b. Now, this other term, if you have only a single middle term, this will be 2 times h by 2, so it will become h. Now, if we take that one and we put inside, it will be 2 times the midpoint. So you can see that it's actually the composite trapezoidal rule that we are using here, but with 3 points. We have the end point and a midpoint, only one midpoint. And this is the formula that we are using, this one. I hope it is clear. So this is the rule. Because our interval is 0, 2, 1, 5, and the midpoint is 0, 8, 5. It's only 1. We are only using 1 midpoint and 2 endpoints. So the total number of points here, we have 3 points, right? So 2 sub-intervals, a total of 3 points. So these are the points that we are using. So this is our composite Simpson trapezoidal rule, sorry. Composite trapezoidal gives us this result for h, right? So our h, we are using 0.65, which is this one. You can see we are using 2 sub-intervals. So 2 sub-intervals, a total of 3 points. Okay, so this is h. Now the second step now will be to halve this h and recompute this formula, but with half h, right? So now if we halve h, you can see we take 0.65, we halve it, we get this, right? And now if we do that, if we halve, it means that we are doubling the number of sub-intervals. So meaning that there will be, instead of 2, there will be 4 sub-intervals. If there are 4 sub-intervals, how many points? 5 points. 5 points in total. So you can count 1, 2, 3, 4, 5 points. And there are 3 interior points. 1, 2, 3. So the interior points are double. Of course, if you keep the factor h by 2, of course, they are double, right? And the endpoints here are not double. That's why you have this expression. So I'm explaining it so that you will not be confused to ask, but which formula are we using? Here we are using the composite trapezoidal rule. Now, if you compare the result, this one and this one, you can see that the second one will be more accurate compared to the first one. Now, we can use the formula, this one, the technique, our Richardson technique here, you can see. We take the beta estimate will be more plus 1 by 2 to the n minus 1, more accurate minus less accurate. So this is the formula. And why 2 to the n? Because of the ratio, right? It's a ratio of 2 by 1. Ratio of 2 by 1. Therefore, we use that 2 here. Okay, so now 2 to the n. Okay, now what is n? What is n? Let me make that precision. N here in the formula, I think I did not mention that. N here stands for the order of accuracy of the original method, this n. Unfortunately, it's not mentioned here. But it's this one. You can see here, the error term is big O h to the 2. That 2 is the order of accuracy. That is the n we put here. It is not the number of iteration, I mean, the number of sub-interval or whatsoever. No. Please write it somewhere, write it down so that it will not create confusion. So that it will not lead you to confusion. Yeah, so it was not specified, but this n is that. It's the 2, the order of accuracy. Okay, now if you substitute 2 to the 2 is 4, and 4 minus 1 is 3. That's why here we have 3, right? Because n is 2, 2 to the 2, 4 minus 1, 3. Right. Now, this is more accurate, which is the second one, this one with the smaller h, plus more accurate minus less accurate. So you can see that the more accurate, the value we use here is the one that we repeat here, right? Minus less accurate, which is the first estimation, this one, 0.66211. Now, if you perform the computation, this is what we get, right, from the Romberg method. Okay, so what we have just done here, we can repeat that process. We can repeat the process. So if you look at the values here, you can see that 0.66211 is this entry in the table. Now, when we have the value here, the next we obtain is this one, 65947. 65947, this one. And if we proceed another time, that is, we halve h again, we get this. We halve again, we get this. So that's what we get. All right. Now, when we come here, next here, what we do, we take this, we use a we use these two, 1, 2, and we compute this one. Then we use 1, 2, and we compute this one. 1, 2, and we obtain this one. And then for the next column, we come to this one, we use these two to compute this one. And then the following two, this and that, to compute this. And for the last column, we take these two, 1, 2, to compute this. And once we are left only with one entry, we cannot proceed. So you see that here, we perform this a certain number of times. Once we are done, we use these values from the first column to compute the value in the second column. And then we use the value from the second column to compute the values in the third, and then those of the third to compute the value in the fourth column. So that is the Romberg integration technique. Okay, at this stage, is there any question? Is there any question? Okay, what I will ask you to do as a homework is to try to generate this value to make sure that you understand the procedure. I'm asking you to generate this. I think it will be better even to stop here to give you time to go and do this, because I don't want to add this for the situation to become a bit more complicated. Is there any question, any concern? So I think it would be better to stop here. And I'm mindful of the fact that I'm giving you the remaining 25 minutes to go through the computation yourself, so that it will be clear that you have time. I want you to check and redo that. Okay, so please inform the student that tomorrow morning, because we have a class tomorrow, but that class will be, I'm hereby dismissing tomorrow's class. So our next class will be tomorrow. So it'll be Friday. Because Thursday we don't have class. Okay, so the next class will be on Friday. So please go do this. Go through that table. Make sure that you obtain exactly the same result. On Friday, I will catch up, right? I will catch up. Meaning, on Friday after my class, normally, do you have a class after mine on Friday? Class rep?
We have, Doctor.
Sorry?
We have modeling.
Okay. Okay, but anyway, what I might do, I think I will record a video before the one of Friday to catch up tomorrow's session. All right. So in the tomorrow is Wednesday.
Doctor?
Yeah.
So the notes that you share with us, where are they on the e-learning?
Can you speak louder, please?
Doctor was saying the notes that you are sharing now, where are they on the e-learning?
The notes. I uploaded the notes here. Okay. Send me an email to remind me to upload it on e-learning, but I shared. Oh, you mean the second chapter? So
Yes.
you mean I didn't? Oh, you're right. So I forgot. Yeah, you're right. Okay, I will do that. I'll first upload it here and then on the. Thank you for reminding me because I didn't.
Okay, sir.
Okay, so I will do that. I will upload this. I will upload the notes here and then on the e-learning platform. Okay, so I repeat what I said before Friday. Tomorrow afternoon or Thursday we don't have a class. I will record a session to catch up tomorrow's session that will not take place because for some reason that there will be no class tomorrow. Please, class rep, disseminate the information on your WhatsApp group to inform the other students. Okay, that there will be no class tomorrow morning. There will be no class, but the session I will record. I will record a 1 hour session to cover what we're supposed to cover tomorrow, and on Friday I will go through again, revise, and also the second tutorial. Apparently, I haven't released the second tutorial. That's something I will be doing also by tomorrow, by Thursday, right? Please, class rep, send me an SMS to remind me about the notes and tutorial 2 because I need to already upload it. Are we together?
Yes, Doctor.
Okay, thank you. We'll stop here for today. Thank you for your kind attention.
Dr. Nyose?
Yes.
Can you please repeat what you said? Sorry.
Oh, you were busy, yeah? You were distracted.
No. When Sir was talking, my internet was glitching, so I couldn't get Sir.
Okay, I was asking you, please send me an SMS to remind me about the courses, the note to be uploaded plus tutorial 2.
Okay, Sir.
Right, okay.
And
I hope,
Sir,
yes?
any update on when we're going to get test 1 results?
Oh, test 1.
Yes.
Next week. Next week,
Okay.
you'll get it next week.
Okay, thank you.
Okay, guys. I wish you all the best for the rest of the day. God bless you and see you on Friday. Or for those of you who will be online during the recording, see you then. Bye-bye.
Bye, sir.
Bye, Doctor.